Okay, thank you very much for the introduction, Dominic. So the title of the talk today is Properties of Learned Convolution Filters, and I'm a PhD student under the supervision of Jannes Kuiper. So this is basically a joint work from us. So the outline for today is I want to quickly rebrush your knowledge on convolutions and convolutional neural networks. Then I will go to the motivation of this work, and then we'll have two large parts. The first one is a large-scale analysis of convolution filters that form in the wild. And in particular, we'll look at the quality of convolution filters and at distribution shifts in the patterns or structures that these filters form. And the second large part is convolution filters under adversarial attacks and how they look if you try to mitigate these attacks. And lastly, just to reward you for your patience, I will present some tools that are hopefully useful for you in your research. The works that I show today are based on two papers. The first one is CNN FilterDB, which we have just presented a couple of weeks ago at the CVPR orals. And the second paper is Adversarial Robustness through the lens of convolution filters, which we've also presented at CVPR this year in the workshops. Okay, so let me start with convolutions. The idea is you have some kind of input image and you apply a spatial transformation for it. So you slide some filter over the image and you aggregate the receptor fields and you end up with a new image. In this case, you have an input image of a person and then the input filter would detect the edges in that filter. And you can do convolutions in various ways. So you can vary the shape of the filter. In this case, it's a 3x3 filter, but it could be larger. You can vary the stride, so the step size of the filter. You can apply dilations and so on. But the very basic principle is always the same. You slide your filter over the input and you produce a new output. So convolutional neural networks actually take this to the extreme. And they apply multiple convolutions to every input. And then they keep aggregating this through the depth. And you end up in total with millions of convolution filters that process your input into some kind of latent space where you can then do further transformation. For example, if you try to detect or do classification tasks, then you will apply some kind of classifier that will separate your latent space into the different classes. And the interesting thing is that you can use CNNs for a lot of things. So they support a wide range of tasks. Here are some common ones. Basically, classification is very common, just detecting what you see on an image. Then there's object detection, where you try to localize objects in your image and also classify them into categories, or segmentation, where you try to outline different instances of objects. A bit newer is also image generation, where you try to produce artificial images that network has never seen. So you maybe see it already from the image source. The website is called thispersondoesnotexist.com, and this is a face that is purely generated by a CNN, and it looks nothing like the training images. And one last application I want to show you, there are of course many more, is style transfer. Here you have an input image, for example, a photograph of Amsterdam, and you give it a style image, which is in this case an image of a house in winter. And then you ask the network to transform the original input image into an output image that mimics the style. So in this case, you see Amsterdam in winter. And surprisingly, CNNs also work on a very wide range of images. So from people's faces to cats to photos of plants, it supports a very wide range of applications. And interestingly, it also works on images that do not carry color information. So for example, it works on depth maps, which you see on the lower right, where you try to estimate the depth to an object. Or on the top right, you see thermal images, where the images do not contain color information in the pixels, but thermal information. Or on X-rays, where you have information about the density of the object. Or even seismic plots, which we have also seen a couple of weeks ago in the presentation of Mario. So one problem of CNNs, however, is that they are very hungry for data. So to typically recognize a class, you need tens of thousands of images. And if you're a small company and let's say you're trying to do some end-of-line tests where you detect damages to some screws, then you probably won't have tens of thousands of images of defective screws. So you're literally screwed. A solution for this is to actually pre-train your model on a very large amount of generic images that are as closely related to your image as possible, and then to fine-tune the model on your actual data set. So that way you can reduce the amount of images that you really require, and this is of course because data is very scarce. Now, interestingly, it's kind of intuitive that you can pre-train your network on data that is very similar to your image, but it also works on cross-domain. So, for example, you can train a neural network to do transformations on seismic images, and you can pre-train it on ImageNet. And ImageNet just contains photos that are natural photos, so photographs of various objects. They look nothing like seismic images. They probably won't even have similar textures, but still pre-training with ImageNet helps you to classify these seismic images way better, and they improve the final accuracy. And the question is why? Because, again, the images are entirely different. So to study this effect, we have established CNN FilterDB. And for this, I try to collect as many different CNNs as possible. So I downloaded everything I could find on the internet. We have roughly 650 CNNs. And we made sure that they are as heterogeneous as possible. So they were trained for different tasks, which of course include classification, object detection, but also more exotic ones such as depth estimation or image generation or other tasks. We also made sure that these models are trained on as many visual domains as possible. So we have categorized them into 16 different visual domains. This includes natural photographs, but also X-ray images, depth maps, astronomic photos, seismic data, all kinds of data. And in total, we have 71 dataset combinations that were used in these models. So out of these models, we then just extract the convolution filters and analyze them. And in total, we obtained 1.4 billion filters. We have limited ourselves to convolution filters of the size 3 × 3 because that's the most common size. And the data is already very large, so it was already hard to process that. And for every filter, we also have an annotation about the source model. And the questions we wanted to answer is, what are the shared similarities in these filters and what are differences? So one of the first things that we noticed is a difference in filter quality. And what you see here is a ResNet 18 that was trained on Cypher 10. So it's a very simple data set. And every row represents one convolution one convolution layer. And the top row is the very first layer. And as you go deeper into the network, you also go deeper in this plot. And here you see the very first 32 filters of every layer. The brighter the colors, the larger the weights of those filters are. And you may notice that if you go into deeper regions of the network, filters become suddenly very sparse. So you have a lot of filters that actually do very minor transformations in terms of the magnitude, compared to only a handful of filters that actually do valuable transformations in terms of magnitude. And we have also seen that you can actually prune away large amounts of these filters and still retain the accuracy. So this means a lot of filters here are degenerated. They don't really do anything, and you could drop them. The other thing that we have noticed is that some filters appear highly repetitive in their pattern. So in particular, in the very last 3 rows, you see that the filter pattern is repeated over and over. And it's less intuitive than sparsity, but it also kind of seems weird and makes us wonder if you really want to have such repetitive patterns, or if this is also a kind of degeneration of filters. So we tried to quantify these quality issues, these generations, and we have established 2 metrics to do so. The first one is sparsity, and that simply counts the amount of inactive filters in a convolution layer. Basically, we determine a filter as inactive if all the weights in that filter are below a certain threshold. And the second metric that we have is variance entropy. It captures how different the filter pattern is. To do so, we do a singular value decomposition, and we measure the entropy of the variance that we obtain on the principal components. And the intuition here is that if you have a high entropy, then you have a uniform variance distribution, and you have a wide range of patterns. They're almost random. But if you have a very low entropy, you have one principal component which dominates all the other components, and then you have a very repetitive pattern that can be described by one component alone. So our first intuition was that this degeneration might be related to overparameterization, meaning your network is way too large for the data that it processes. And indeed, we compared 3 data sets with different complexity. The first one is Cypher10, which is a very easy, low-resolution data set. The second one is Cypher100, which is slightly more complex, but also low resolution. And the last one is ImageNet1K, which is higher resolution or medium resolution by today's standards, but significantly larger than the previous 2, and also contains more images and more classes. And if we look at the sparsity throughout the depth of the model, we see that it stays almost 0 for ImageNet throughout the entirety of the depth. But if we look at Cypher10, we see that roughly after 20% of the model depth, that sparsity explodes. And basically, the layers don't really learn anything, except for very few filters in that layer. We see a similar effect in Cypher100, slightly delayed. So that one starts at roughly 50%, where the model becomes sparse. So our conclusion was that overparameterization indeed increases sparsity and leads to a type of degeneration. We can't, of course, say that this is the only cause of degeneration, but it's at least one of those. We did the same experiment with the variance entropy, and we get similar results. If we look at the entropy, then it's relatively comparable in the first layers, but as we go deeper into the model, the ImageNet filters retain a kind of variance that shows that it actually learns different transformations, except in the last 10% maybe. But for Cypher10, it quickly dips away and the layers learn the same filter over and over. And again, we see the same effect also for Cypher100, just slightly delayed. So again, we conclude that overparameterization decreases entropy and is a cause of degenerated filters. Now, the second part of our analysis really focused on understanding how different the filter patterns are that the models learn. Because apparently you can transform your input samples on a model that was trained on ImageNet similar to seismic data. So there must be some shared patterns. And to study this, we've made the following protocol. First, we took all filters, we individually normalized them by their L-infinity norm, such that we only compare the pattern and not the scale. And then we applied a singular value decomposition to all filters in total, so that we have a description of every filter on the same filter basis. And this allows us to describe each filter as 9 coefficients on the obtained basis. So we see an example, this distribution, if we look at multiple filters in total, we get groups, and then we get these distribution plots. So basically we plot the distribution of every coefficient for a selected group of filters. And then we can, of course, go ahead and compare these two distributions by the Kullback-Leibler divergence. And we did a slight twist to it. We did a modification such that it becomes symmetric, just so we don't have to deal with symmetry issues. And then we compute the Kullback-Leibler divergence on every coefficient, and we weight them by the amount of the variance on each coefficient, and then obtain a distribution shift measurement. So for the results, we have shown this in heat maps. Dark colors here indicate very similar distributions, and bright colors indicate very different distributions. And dark colors mean a KL divergence of 0, whereas brighter ones go towards infinity. And so what we did is we grouped all the filters by the learned task of the model in the first analysis, and we compared the pairwise KL divergence. And what you see is this checkerboard pattern. And the pattern itself is not so interesting, but what's interesting is that the divergence between different tasks here is relatively close to 0. So it means that independent of the task, the filters look very much alike. So in theory, this means a classification network learns the same thing as a super resolution network or an image generator, which is quite surprising. Now, the second part of our analysis was what happens if we split the filters by the visual domain of the data set. And here you see is something different. So you have in the top region one large black part of homogeneous visual domains. This includes natural photographs, but also thermal images, seismic data, faces, and then you have outliers. Sorry, and the outliers, if you look at them in detail, are highly related to medical domains. So we have medical CT images in the outliers, we have medical X-ray images, and medical MRI images. And if you look at the coefficient distributions of those domains, you'll see that they are very spiky, as shown on the right. And these spikes actually indicate, again, a type of degeneration, mainly a very repetitive filter pattern. And we assumed that this is because of overparameterization, again, because data is very, very scarce in medical domains. It's very expensive to get new data. And we assume that these models simply overfit to the very few samples that they have, and therefore have these degenerated filters. So again, we conclude that most visual domains are very similar. There are some outliers, but the outliers are not necessarily caused by the distributions themselves of healthy convolution filters, but mainly by the very large amount of degenerated filters that we see in these models. So we assume that if you would actually remove all the degenerated filters, this entire heat map would be pretty black and would be very homogeneous again. And then there's also a long established theorem in deep learning that actually states that convolutional neural networks, in the beginning, they all learn the same, but as you go deeper into the model, they tend to specialize. And so we try to see, do we capture this with our metrics? And the answer is not really. So if you look at the convolution depth and you separate the filters by the extracted depth, then most distributions are very similar. In fact, there is a slight difference in the very last 10% of the model, but we again think that this is mainly related to degenerations rather than fundamentally different coefficient distributions there. So in terms of the representations that these layers learn, they are very similar across the task, across the visual domain of the data and the convolution depth, which is quite interesting. However, if we compare different model architectures or model families against each other, such as CycleGAN versus DenseNet versus VGG, we actually see distinct distributions. So, for example, DenseNet and VGG have two entirely different looking distributions, but if you look inside a model family and compare two models of the same family, just different architecture, such as VGG 13 against VGG 16, those are very similar again. And in fact, we have a large amount of ResNets. I don't have an image for this, but we plotted those ResNets against each other. And we saw that even if you train the ResNets on different tasks, on different visual domain, again, they appear to form very similar filter distributions, which again backs our hypothesis that tasks and the visual domain does not really influence the distribution of the filters so much. We also try to understand where the differences actually exist, because if you take two models and compare them against each other, you will see differences. You just don't see differences on average over entire tasks or visual domains. And it turns out the location where the shift is entirely different depending on the task. So for example, if you look at segmentation models on the top right, you see that the deeper you go into the model, the more differences you see in the filters, which is what you would also expect. But if you look at object detection models, you see the entire opposite of that. You see very many differences in the filters in the first layers, and then marginal distribution shifts in the upper layers. For style transfer, for example, you see a U-shape, which comes from the network architectures that is primarily used there. And for face detection, you have a large amount of early layers that have a high distribution shift, so until roughly 40% of the model depth. And then afterwards, they seem to learn very similar things again. So that seems quite interesting. The next thing we try to understand is, do the filters come from the same basis, or can they be described by this, the same basis? So, because previously we mapped all the filters to the same basis, and it turns out, yes, you can. So independent of how we split our filters, if we do this by the task, by the data set, by the model depth, these obtained filter bases are always very similar. There might be cases where a component is inverted, but this can be simply symmetricized by inverting the coefficient distributions. And you also see differences in the explained variance, but the components themselves and the pattern of those is very similar, independent of the split. So what are the implications of this? The implications are that as long as you pre-train your model with large amounts of complex data, it doesn't really matter what type of data it is. In fact, there is works where they pre-trained models with generated images of fractals, or at CVPR, I've seen one paper where they pre-trained models with noise. And that seems to work as long as, again, you have a lot of data and that data is complex enough for the model to actually learn something. the second part, or the second implication, is that models with many degenerated filters will probably not be very well suited for transfer learning, because if you have sparse filters, they will block the gradient flow. And if you have repetitive patterns, they won't easily adjust to your new distributions. So we have found a lot of these degenerated filters in public models that are used for pre-training. So we suggest that you really take a look at the source model if you use transfer learning to understand if this model is actually suitable for pre-training, because if it has too many degenerated filters, you will probably want to look at something else. All right, so this was the first part of our analysis. The second part is focusing on adversarial attacks. And we had a presentation about this in this seminar at the very beginning of this year by Julia. But just a quick refresher. So adversarial attacks are attacks on the input images such that they fool the network to generate an entirely different output. So for example, let's say you have a self-driving car and it wants to recognize these street signs. So if you show it a stop sign and you train your model, it works well, it will recognize that stop sign. But there exists a noise that you can apply on top of that stop sign that will force the model to detect that this is a yield sign, and it will detect it with a very high confidence instead of a stop sign, even though that this perturbation here is barely visible to us humans. This is of course very dangerous in safety critical domains. In particular, there has been works that show that you don't even need to find these weird, almost noisy perturbations, but it's sufficiently to use a patch of black tape and place it in a strategically important position, and then you can fool the network already. So the current way of dealing with this is adversarial training. And the idea here is you simply try to find the worst case perturbations during training and re-inject it to your training data. You basically tell your model, hey, you made a mistake there, fix it. And that works very well. It gives you a great accuracy against those adversarial attacks, but it heavily increases the training time because you have more data, and it's also very expensive to find these perturbations. So there is actually a common benchmark, which is called robust bench. It benchmarks robust models on Cypher 10, Cypher 100, and ImageNet against each other. And we downloaded 71 of those checkpoints. We extracted the architecture, trained the same architectures without adversarial training, and compared the differences in the convolution filters. We wanted to understand what the differences are, and again, where they are located. And we simply used the metrics that we have previously shown. But in this work, we wanted to remove the amount of degenerated filters. So we removed the bottom 10% of the filters, and we select those by the magnitude. So first, we looked at where are the distribution shifts between robust and normal models. And it turns out that there are two interesting locations. You have this at the very beginning, and particularly very dominantly in the very first layer, not so much in the second or third, but explicitly in the very first layer. And then the drift also increases in the later stages, which is not that surprising, perhaps. But the second observation that we see here is if you, again, compare different data sets, you see that there is a large shift between robust and normal models on very easy data sets, such as Cypher 10. But that drift actually decreases if you look at Cypher 100, and it's even further decreased if you look at even more complex data sets, such as ImageNet. So we again started by visualizing the filters and comparing them side by side. And we did this for the very first and the very last convolution layer. And if you look at the first layer, it's not surprising that the normal training or the standard training leads to a diversity of filters that do some kind of transformations, whatever that is. But if you look at the filters of adversarially trained networks, they have entirely different filters. In particular, only the center weight is activated there. And this is interesting because this could, in theory, be simply replicated by a convolution with a 1x1 filter. So the majority of weights there are not really used. And if you look at the last layer, you see what we have seen before in overparameterized networks. So standard training has these repetitive filter structures, but adversarial training improves that pattern diversity. It has slightly more different layers. So we wanted to understand what these type of filters in the very beginning actually do. And unfortunately, this is on Cypher 10, so the image is very low resolution. It's 30 times 32 pixels, because this adversarial training is so expensive that researchers really focus on low resolution data sets. And here you can see an image of a cat, and in front is a human wearing a jeans and a shoe. So we looked at what happens if you do a normal activation versus an adversarial activation. So what is the purpose of these filters? And then we just plotted the difference against each other. And what you can see is that these filters are apparently, in combination with the activation function, very successful in removing the perturbation in certain parts of the image. So in this case, it removes the perturbations from the leg, but also from the cat, which seems to be distinct properties of this image, and the noise in the background is retained. So this, of course, then is a kind of pre-processing of the image that the network has learned to eliminate perturbations from regions of interest. So now that we have that, we have also, again, looked at filter quality. Again, we used the same metrics as we used before, but we have included one more, and that's orthogonality. With this, we try to capture how different the, not the filters are, but the feature maps that are produced by filters. And we did this by computing a dot product between filter stacks, so a 3D version of the filters, and we simply treat them as vectors. And if you measure the orthogonality and you see that two 3D filters are actually orthogonal, this should mean that they also create very different feature maps. And we did, again, the experiments over the depth of the model. We did it for every data set, and we, again, compared robust versus normal models. And you see what I've previously also shown you. The sparsity is very high for Cypher 10 models that are relatively or that are normally trained. It significantly decreases if you do adversarial training. For Cypher 100, you also have sparsity, but it's lower than on Cypher 10. And on ImageNet, you barely have any sparsity, even if you compare normal between robust models. For the entropy, you see that the entropy, again, dips off as you go deeper into the model. And there is a large drift for Cypher 10, a medium drift for Cypher 100. And on ImageNet, there is a barely imperceptible drift. And for orthogonality, we see slightly different things. So we see that on Cypher 10, the orthogonality of feature maps increases, but eventually will dip off. We again see the same thing for Cypher 100. And adversarial training seems to correct this. So adversarial training seems to generate feature maps that are more orthogonal to each other. For ImageNet, however, we see that it never dips off. And again, the gap between robust and normal models is very low. So our conclusion was that robust models that are trained by adversarial training actually form diverse, less sparse, and more orthogonal convolution filters. But we weren't really able to pinpoint why. So apparently the dataset complexity itself causes better filter quality. And if you think about adversarial training, what it does is it actually introduces new data to the training. So it seems natural that you reduce the overparameterization. So it's unclear if this improve in filter quality is actually a sign of robustness or if it's simply a side effect of adversarial training. And if it is not a side effect, then we should be able to add regularization to the filter quality and simply improve robustness by enforcing that the network trains orthogonal high variance filters with low sparsity. So in summary of the entire talk today, we've did an analysis of 3x3 convolution filters on a diverse model zoos. And we have seen that if you compare individual models, they will form distinct filter distributions, and so will families. But if you compare the average on the task, on the visual domain, or the convolution depth, then the distributions become largely similar. The other thing that we have seen is that many CNNs contain degenerated filters, and you should be aware of those during transfer learning. And the last point is adversarial training seems to improve the filter quality, be it a side effect or not, and produces very distinct first stage filters. So as promised, I also want to show you a couple of tools that you can use in your research. These are GitHub repositories written in Python and developed for PyTorch. The first two in the top are the repositories for the papers. The first one also contains the full data set of extracted filters, so you can download it. It's basically one large NumPy array, but every filter also has an annotation. So you can run your own experiments and do your own filter analysis with that. The adversarial robustness repository also contains all the code that we've used, so you can look at the metrics and use our visualization tools. On the left bottom, I have a little framework that you can use for your CNN training. It has, unfortunately, the title pre-trained CNNs because that is what it initially was, but it has grown into a framework that I constantly use in my research. So it has a lot of architectures implemented and also some regularizations. And perhaps it's something you can use. And the last library that I want to mention is TorchConf quality. We've gotten a lot of feedback at CVPR that we should release our filter quality metrics as a standalone library so people can test their models and they can also understand the convergence of their models during training. So we did this, and this is the library. It's a very small, simple library. You can include this in your training and understand what your model and learns and how it learns. Okay, so we're at the end of the presentation. I thank you very much for your attention.